Welcome back, all of you. We have been discussing NOE since last two classes. Of course, we discussed very fundamental concepts of what is an NOE. We knew NOE is change in the intensity of the one nuclear spin when other nuclear spin is irradiated. Basic requirement for this is the two nuclear spins should be close in space, and it depends upon the distance. It goes by inversely as r power 6. As the distance increases slightly, there is a drastic change in the intensity. There is a drastic reduction in the intensity. So when this NOE phenomena you can think of happens when one spin is irradiated. That is like, for example, while doing the decoupling. The change in the intensity could be positive or negative. That is more or less. This is phenomena called positive NOE or negative NOE. The dominant phenomena mechanism for this NOE is the dipolar relaxation pathway. And then we also saw that dipolar interaction is the dominant thing. And then we understood basically how cross relaxation pathway, cross relaxation phenomena aids in getting positive NOE or negative NOE. We consider two spins which are closed in space. We irradiated one of the spins with low power RF for a short time, and when the spins attained thermal equilibrium, new thermal equilibrium, immediately after that we measured the population difference while irradiating. We found there is no change in the intensity when the spins follow single quantum relaxation pathway W1s. That is the probabilities of transitions. W1 is a transition probability for single quantum. So there was no change in the intensity. What we did is we brought in cross relaxation pathways, like for example, instead of double quantum, instead of single quantum pathway, what happens is the spins attain different equilibrium state by going through a different pathway like relaxation, like double quantum or zero quantum. Then we worked out what is the change in the intensity when it follows W2 probability, that is double quantum probability, when that is higher. When we measured the change in the populations between different energy states of the other spin which is in close proximity with this irradiated spin, we saw 50% enhancement in the signal intensity. Whereas we also found out what happens if the dominant relaxation pathway is W0, that is alpha beta to beta alpha transition, that is W0 transition, zero quantum. We found there is a reduction in the intensity by 50%. So what basically we try to understand is, depending, there are all the three processes are not competitive processes. There is no none of them are exclusive. Not that only W2 is present, W0 is present or W1 is present in the molecule. They are, even everything could be possible. They are competitive processes. But now the thing is, which is dominant mechanism that defines whether it is a positive NOE or the negative NOE. We observed that, and which is the dominant, and W1 is dominant, let us say, zero quantum relaxation pathway. Then we saw that there is no way you can see NOE. Detection of NOE is less probable. You will not see it also. So W2 and W0 are the requirements we have found out. And then we correlated this with the spectral density function, and also tau c, the size of the molecule. And we discussed that tau c also tells you about the sluggishness of the molecule. How fast the molecule is undergoing motion, whether it is fast motion or slow motion, defines the frequencies, and which defines whether it is W2 is dominant or W0 is dominant. So all these things we understood, and we came to a situation to understand, if we want to know the tau c, when we correlate with this molecular weight, general rule of thumb was tau c in nanoseconds is approximately equal to 0.6 times the molecular weight, approximately 50%, slightly more than that, 0.6 times the molecular weight. So, and try to see what is going to happen. For a small molecule I consider, with the molecular weight of, let us say, 3.3 kilodaltons, and we found out tau c is about 2 nanoseconds. Simply calculate this. This corresponds to 500 megahertz. On a 500 megahertz spectrometer, then this is dominant. W1 is dominant. So that's what I am going to tell you. The tau c depends upon the molecular weight, which in turn depends upon the frequency that is going to be produced, that is tau c in nanoseconds, and that depends upon which frequency omega 0 you are doing the experiment, and then that tells you whether NOE is positive, negative or 0. Okay. This is what we discussed. Now let us consider the spectral density twice the omega frequency, twice the Larmor frequency for small proteins and other molecules. Then what happens, especially for small molecules, at twice the Larmor frequency, let us say 500 megahertz if you are considering, then 2W, that is 1000 megahertz, is generally absent. So that means what is the relaxation pathway? We can find out what is the relaxation pathway for that. It is, so when that is absent, only W at the Larmor frequency, whatever you see, that is dominant. The zero frequency component of the spectral density function then increases because of this. Finally, we found out W2 minus W0. So when this increases, it increases the molecular weight. See, the rotational frequency becomes lower. This is the important concept. So we also discussed JW. What is JW? Spectral density function. It depends upon tau c and omega 0. And simple equation without working out I am giving you. JW depends upon twice tau c or 1 over omega square tau c square. So omega tau c is what is important. Okay. Let us say if omega tau c is 0, then JW is twice the equal to twice of the correlation time. So it's like that you can work it out. Now what it implies, this equation is, you can calculate, it has a maximum at omega is equal to 0, and the spectral density drops off very drastically at higher frequency, falls off very easy. And so the spectral density, how fast it is dropping off, how fast it is reducing over at higher frequencies, is controlled by tau c. You understand? JW depends upon two factors, tau c and omega 0, which is given by this, and at omega 0, omega is equal to 0, then spectral density drops off, it is actually maximum, and afterwards it drops off to higher frequency. So how fast it drops off, everything is controlled by tau c, that molecular correlation time. But what is the total amount of the oscillating field? This is what we discussed earlier also, that remains constant. The upper limit only is the one which changes in the correlation time, but the total correlation amount of the oscillating field that is produced at the site of the nuclear spin remains same. That cannot change, because, and that defines the frequency. But what is happening is the upper limit of the frequency is the one which vary with the correlation time. That is why this equation, this graph, I showed this when we were discussing the relaxation phenomenon also. This is JW, spectral density function, and this is what we saw, and omega tau c is very much greater than 1. This is the intermediate condition where omega tau c is approximately equal to 1, where you see no NOE, and this is omega tau c is very much smaller than 1. Now you will see we have certain conditions under which we can see NOE or not. Let us see omega tau c is less than 1. When omega tau c is less than 1, the molecules tumble very fast, and this is a situation we also discussed. The molecular motions are fast. We discussed for small molecules it happens, positive NOE. Remember in the previous class we discussed for small molecules which tumbles very fast, omega tau c, if you calculate, is much smaller than 1. As a consequence, NOE is positive, and this condition is called extreme narrowing condition. The extreme narrowing condition is experience. You are going to see this extreme narrowing condition only for small molecules, and especially these things in non-viscous solvents. When the molecules you put in non-viscous solvents, then if it is a viscous solvent, of course mobility is less. Only non-viscous solvent if you put, molecules undergo tumbling motion very fast, thermal agitation is going on. because of this fast tumbling motion, NOE is positive, and this is the situation we encounter. Now, when omega tau is larger than 1, greater than 1, what does it mean? Molecule is tumbling very slow. That means there is a negative enhancement, negative NOE you are going to see. This is called diffusion limit. Okay, when this can happen? The diffusion limit can happen only for big molecules like proteins, in the sense large molecules. So, it cannot rotate faster like small molecule, cannot tumble faster, and then especially such molecules you put it, some molecules you put in viscous solvents, restrict the mobility, in which case you can experience omega tau c larger than 1. It is called diffusion limit. On the other hand, consider a situation omega tau c is approximately equal to 1. This is the limit in which NOE goes to 0. When omega tau c is approximately equal to 1, you will not see NOE at all, and this can happen for neither too big molecules nor too small molecule, some medium sized molecules, and this is at the Larmor frequency. This can happen when tau c and omega is approximately, tau c is approximately equal to Larmor frequency, then this turns out to be 1, then you are going to see this medium sized molecule, this you can experience this and you do not see NOE at all. So, omega tau c is equal to 1 is a situation NOE goes to 0, you do not see NOE at all. And the dependence of NOE on omega tau c is given, of course, this is taken from this book, you can see from this paper, you can see that this is an example of a proton-proton NOE. How NOE depends upon omega tau c. And this is the NOE in this axis, it is the intensity of the signal, that is the NOE that is measured, it is given by eta maximum NOE we saw is plotted as a function of correlation time omega tau c. Now, see the molecule like this, for example, large molecules are at this side, small molecules are this side. For small molecules, if you are in this range, you get 50% NOE. That is another thing, very, very small. And then as you keep crossing this omega tau c limit, then it is a negative NOE minus 100. This is for the large molecule. So, once you cross this omega tau c, which is equal to 1, which is the condition where there is no NOE, then you are going to the higher side, it is a large molecule. This can happen for large molecules in high magnetic field, and this is minus 100%, that is minus 1% enhancement, minus 1 we call 100% enhancement of the signal intensity. So, this is 100% or this is 50%. Is the negative NOE, this is a positive NOE. This can happen for small molecules in low magnetic field. This region comes to the big molecules in this high magnetic field. This is the situation we always come across when you are dealing with NOE. So, this please remember, it depends strongly on omega tau c. That is the important concept we should remember. So, omega tau c and tells you, and of course, omega means depends upon the magnetic field and also size of the molecule. So, small molecules at low magnetic field gives rise to positive NOE. Big molecules at high magnetic field give rise to negative NOE. This is the important graph you should remember. And NOE also depends upon the distance, we said 1 over r power of 6. Of course, we can calculate NOE also. We can do the experiment and find out what is RIS, etc. We will discuss those things later if there is time. But remember, the strength of the NOE depends upon Ri to the power of minus 6 for a dipole. But dipole interaction depends upon the inverse cube of the distance between two interacting spins. That is a dipole coupling. The dipole coupling depends upon 1 over Rij cube, where Rij is the distance between two nuclear spins I and J. But now we are dealing with two nuclear magnetic dipoles for NOE. So, NOE depends upon the strength of the two dipoles involved. As a consequence, W's depend upon r I to the power of minus 3 into r I s to the power of minus 3. So, it become r to the power of minus 6. So, NOE is strength of the NOE depends upon inverse 6th power of distance between the two spins I and S. Important point. So, that is the reason why slight deviation from the distance, if you change is r little bit, because r power 6 in the denominator. So, this will drastically decrease the intensity. So, it is a very sensitive parameter, r power 6. So, this is the equation which is given with the enhancement of signal intensity. W is given by r to the power of minus 6. R is the distance between the two dipoles, that's two nuclear spin that separates, and JW is also spectral density. So, this is also depending on spectral density. So, enhancement in the signal intensity depends upon R and spectral density together. So, we are discussing, remember at one stage we said it depends upon the ratio of the gammas. What happens if you consider a homonuclear case with identical gammas or heteronuclear case with different gammas? How does the enhancement affect, or what will be the enhancement? Let us see. For homonuclear case, of course, we know gammas are identical. The maximum NOE gain you get is 50%, remember. Maximum NOE in the homonuclear case is 50%. On the other hand, for heteronuclear case, it goes by the gyromagnetic ratios. The gyromagnetic ratio gamma of two heteronuclear spin dictates the enhancement in the signal intensity. Okay. This is the formula which you have to use, gamma A by gamma x, 2 times gamma x. Okay. So, both are identical. Let us say homonuclear case, it is half, 50% intensity. On the other hand, if it is let us say some other nuclei with gamma quite small, let us say gamma 4 times smaller, let us consider heteronuclei. Then you see depending upon which you are irradiating, which you are observing, it changes. So, we will work it out as you go further. When you look at the intensities, you can find out. I mean, one or two example of a proton carbon we will take and find out. So, NOE is very important, especially when you are dealing with heteronuclear case. That too, when one of the nuclei has a low gamma, that means carbon 13, let us say 4 times low gamma, or nitrogen 15 for that matter. Of course, it is a special case, it is the negative magnetic moment also, we will come to that later. Such low gamma nuclei, if gamma A, gamma x is the ratio, when you consider, the sensitivity enhancement depends upon gamma, and it is very important, especially for low gamma nuclei, to enhance the sensitivity. Basically, when we discuss the carbon 13 NMR also, I told you always carbon 13 NMR is experiment is obtained, in a carbon 13 spectrum is obtained, C13 experiment is carried out with broadband heteronuclear decoupling. That is what I said. I am observing carbon 13 spins, I want to get the carbon 13 spectra, but I break the coupling of all carbons coupled to all the remaining protons. Why we do? During that time, we wanted to simplify the carbon 13 spectra to get only single peaks for each chemically inequivalent carbons. But another important factor was there which I did not tell at that time. There is also what is called NOE enhancement. When you do the decoupling, heteronuclear decoupling carbon 13, you are going to have NOE enhancement and change in the intensity. That benefits actually. Okay. So, enhancement of NOE, of course, as I said, is defined by the term eta, which is a gain factor. As I told you, eta is given by gamma A over 2 times gamma x. A is the saturated spin, I am irradiating A, and x is the observed spin. Please remember, there are which nuclei you are observing, which nuclei you are disturbing, how irradiating with RF, that defines the enhancement in the intensity, because these two parameters are different here. The total intensity I is given by this thing, 1 plus eta into I0. I0 is the original intensity. So, if eta becomes more, then because it multiplies by that, if let us say eta is equal to 2, then it is 3 times I naught. Eta is equal to 4, 5 times I 0. Enhancement with respect to original intensity depends upon this eta enhancement factor. Okay. Now, I will consider a situation. I am decoupling proton A and observing carbon 13. What does it mean? I am decoupling gamma A over 2 times gamma X. Now, what is my observed nucleus is in the denominator, and this is what I am decoupling. So, what is eta? You know the gamma. So, gamma of proton is 4 times less than that of carbon 13 is 4 times less than that of the proton. So, now I am irradiating proton. Proton is in the gamma A is in the numerator, it is 4 divided by, this is let us say half of that, 1/4 of that. Okay. This is, if this is 4, this I will take only 1 because 1/4 of that. So, this 2 is there already in the denominator, it turns out to be 2. You understand? Gamma of proton is 4 times less than, more than that of carbon. If a carbon gamma I consider 1, this I consider 4. And because it is 2 is in the denominator, it turns out to be 2. That means, if I decouple proton and observe carbon 13, there is a 200% enhancement in the signal. There is huge lot of gain in the signal intensity that aids in speeding up our experiment. Please understand. Now, I am decoupling proton and observing carbon, there is enhancement in intensity by 200%. On the other hand, let us consider a situation where I am decoupling carbon 13 and observing proton. That is something, is the reverse of that. Why we do not need to decouple proton and observe carbon always. You can also do the other experiment. I do carbon 13 decoupling and observe proton. Now, where is this thing? Proton now is the observed nucleus, that is in the denominator. This 4 is denominator now, 1 is in the numerator. Look, calculate this thing, this turns out to be 12.5%. See, when I decouple carbon 13 and observe proton, only 12.5% enhancement in the intensity. Unlike in the decoupling proton and observing carbon, there is 200% enhancement. This is the difference. Depending upon which nucleus you are decoupling and which is the nucleus you are observing, based on that, enhancement factor eta depends, especially in the case of heteronuclei because gammas are different. So, now with this, having said all those things, we want to see how we can measure NOE. We have been totally, all along we have been discussing steady state NOE. I told you about steady state NOE because with the low power RF we are saturating the spins, and the spins attain a new steady state after some time, and they change the intensity what we are going to observe. That is what we said, and we know it is a steady state. So, we have to call it as a steady state NOE. How do you measure the steady state NOE? It is a simple experiment like this, very simple experiment. What we have to do, let us say I am looking at proton, irradiating one of the protons and see the effect on the other neighboring protons. So, we have to selectively pre-saturate that proton with a low power RF continuously. Keep on sending the low power RF continuously for that proton and disturb the spin state of that one, may saturate it, and then that is called selective saturation. Pre-saturation I am doing before, continuously before applying the second detective pulse RF pulse 90° pulse, I am saturating other spin selectively. Then apply a radio frequency pulse and collect the signal. This simple experiment. The simple experiment what we have to do here is simply we have to apply a low power RF and then apply a 90° pulse and start collecting the signal. The low power RF has to be applied for a long time. You should not apply high power RF, then you will disturb the spin system and it will be, you will be completely doing a different experiment like decoupling and you will not see NOE. So, low power RF. In the first experiment what you have to do, the proton is selectively excited and saturated, you obtain a spectrum. That is one experiment. It is something which we have to do. Let us say I am want to see the NOE between two protons, I am irradiating this, that is what I do, and then get the spectrum and measure the intensity of the other one. That is what we have to do. In the second experiment, what we do is we take a reference spectrum, because finally I have to do a difference NOE. What we do is I apply a similar RF but far away, sitting somewhere here, very very far away at half resonance, so that spins are not disturbed. Because RF power, if there is some disturbance because of RF power, that should remain same in both the experiments. So we do off resonance radiation, which is far away, and observe the change in the intensities. Now when I do this experiment off resonance, these intensities are not perturbed, they are not changed at all. So this is called a control experiment. You first do control experiment and then selectively irradiate the peak of your choice. Take the difference between these two experiments now, because in this case there must be a change in the intensity. You will not notice the change in the intensity because you are simply getting the NMR spectrum. But if you want to notice the change in the intensity, there must be some difference you have to see. Only then it will tell you whether there is intensity change or not. So do the control experiment and then do this normal experiment, take the difference, you will find out how much is the change in the intensity. This is a simple experiment routinely done. It is called 1D difference NOE experiment. One dimensional difference NOE experiment. We simply irradiate one of the protons at some frequency and then do the control experiment by irradiate a far away these things so that no spins are disturbed. Take the difference between these two. This is a simple example of this molecule. Let us say we are irradiating one of these protons here. With the irradiated proton, you see, it will be always negative in intensity. You will see that only. So you are not going to observe any signal there. And then this is the normal, this is the spectrum which we have observed. By irradiating this one, we took a one dimensional spectrum. And then look at it, there is all other peaks, intensity is not there, they are far away. So for this proton only this and this are close by, there is a change in the intensity here. But then if what you want to see, you have to do the decoupling and see the change. But here I have already taken the difference, that is why you are seeing. If I do not take the difference, if I give you this spectrum, I am doing the irradiation here, signal is 0, and you see there is some change, but you are not seeing anything here. But what is the difference between this and this? If I give you normal spectrum and spectrum after irradiation with a low power, you do not find much of a difference. Okay, I can always readjust the intensities to see matches with this one, but that is not right. Now I took the difference between these two and this is what you are going to say. When I take the difference between this and this is 0 intensity because it is irradiated power saturated signal, and here because you are subtracting this from this, it will be a negative intensity. And look at it, wherever there is enhancement in the intensity, there is change, the difference is not 0. But here difference is 0, this signal it nullified, all other signal intensity nullified when I took the difference. But especially this peak and this peak, there was a gain in the intensity. As a consequence, when I took the difference of these two, there is no nullification at all. Still there is some signal retained. This is the gain in the intensity. Of course, gain maximum I said 50%. That does not mean you have to be always 50%, but that depends upon various parameters. You see, we have got 30% enhancement here and only 2.3% enhancement in this one. So similarly, you can do heteronuclear NOE. Look at the carbon 13 here, this is what it is. See, for example, some of these things are very very weak in intensity and these protons also. But if you try to do the decoupling of proton, then there is enhancement in the signal intensity. We saw when you decouple proton and observe carbon, we said there is 200% gain. Okay. So this is how we can use this idea of NOE for heteronuclear case to enhance. But there is one peculiar situation we may come across in heteronuclear NOE. Heteronuclear NOE can yield positive signal with for the nuclei with positive gamma like carbon and others. There are certain nuclei with a negative gamma, magnetic moment is negative. For example, silicon 29 and nitrogen 15, they have negative gamma, these two. When you have negative gamma, very interesting thing happens. If you take the ratio, it is negative. That means Sometimes you may not even see the NOE, NOE may become 0 also. Look at the situation for this. A hypothetical case, we are observing proton, let us say, and decoupling proton, observing nitrogen 15, decoupling proton. We are observing 15N while decoupling proton. The decoupling nuclei is always given in flower brackets, you know that. So, without any NOE, the intensity, let us say we call it 1, it is a stick plot. Now, with NOE, now the 100% NOE is there, now it is going to be minus 4, because if you take the gamma of nitrogen 15 is 10 times smaller than that of proton, you work out it turns out to be minus 5. But 100% enhancement also if you take minus 5 plus you add 1, it will be only minus 4, still it is negative, there is not much gain in the intensity for you. If you continue like this, in a situation where there is 50% NOE, you will get minus 1.5. Okay. Whereas, if you consider a situation, NOE and this can turn out to be 0, and let us say there is a 20% NOE. If 20% NOE, if you put here calculate what is the 20% NOE with this, then it turns out to be NOE minus 1. Then in which case, if you take the total intensity of the signal, it turns out to be 0. So, in the negative nuclei with negative magnetic moment or negative gamma, sometimes it so happens when you do NOE, instead of gaining the signal, you will give less signal, or it may sometimes even signal intensity will go to 0 also. So, these are some of the tricky things which you should know. And in the spectrum which is taken from some literature, you see if the nucleus has a negative gyromagnetic ratio like this, some of these nuclei, there is a null signal can be observed under proton decoupling because of this. An example of a situation like this is a proton decoupled, this is a proton coupled silicon spectrum. So, here there is a, see when you are decoupling your signal intensity has gone up, when you are coupled signal intensity has come down actually. So, you can get negative sometimes because of negative magnetic moment. So, silicon 29 intensity may even become 0, it may be negative also. So, depending upon the size and the rigidity of the molecule, tau c of the molecule, steady state or transient NOE experiments are done. I have not introduced transient NOE, we will discuss when we come to 2D NOE after introducing 2D. Since I have not discussed 2D, we will not worry about it. For small molecules or organic molecules, what we can do is the steady state NOE what we discuss now. Irradiate one of the protons and irradiate the off resonance, take the difference. When you take the difference spectrum, you will see the change in the intensity of only selected peaks. With that, you can measure the percentage of NOE. This is the 1D selective transient NOE. Okay, 1D and also you can do the transient NOE similar to this thing 2D. But anyway, I will explain this when I explain the NOE, because NOE I will use the transient NOE there. But quickly I will touch upon this. See 180% before that, you have to apply 180% on one of the spins and give some mixing time tau m, and during this time NOE start building up with using both 0 quantum and double quantum relaxation pathway, apply an 90 degree pulse and collect the signal. That is all the transient NOE experiment in a one dimensional way. And now how the NOE builds up with time, that has to be obtained for depending upon how short the time, how long the time is, and then tau m has to be approximately fixed to be 1 hour T1. So, it will build up like this and then start decreasing. So, these things I need to discuss more about this after introduce 2D. When I talk about 2D NOE, I will introduce transient NOE. Please remember here what we have been discussing. If you look at some of the spectra, sometimes it so happen the signal intensity can be nullified because of when you are decoupling because the negative NOE, negative magnetic moment. As a consequence, when you are doing heteronuclear case, you have to be extremely careful. Homonuclear case, though, there is no issue. Either you will get intensity more or less depending upon the size of the molecule. For the heteronuclear case, it also depends upon gamma, sign of the gamma. So, this is what I just basically wanted to tell you. Since the time is up, I am going to stop, and NOE I do not think we can discuss further. Basically, in this I have given you the idea of what is the concept of NOE. Do not worry, this is only NOE is a huge topic in NMR. There is a book on NOE itself by Nagel. So, there are two books are there on NOE itself on the topic NOE. So such a huge topic. So we cannot cover everything and discuss every aspect of this thing. Basically, I wanted to give the basic concepts and highlights of what one can do. Remember, NOE you can use this to get the distance information. Once you get the enhancement, how much is the enhancement intensity, you can correlate it with the distance and get the distance information. How to get the distance information I didn't discuss. It is all simple arithmetic, you can do that. Most important is the concept and how do you do the experiment I discussed. Rest is simply you have the well known equations, you have to fit into that and then measure the change in the intensity and the R. So this is what it is. But there are certain things here you should understand. NOE, we discussed about only 2 spins we discussed. What happens if there is a third spin present? So it is not fairly simple to understand. 3 spin effect will be there. Third spin also will contribute. Whether it adds or subtracts is a different question. So varieties of problems are there. It is not that we have discussed the example of taking 2 spins that we have understood all about NOE. I just discussed only about the concepts, mechanism of NOE, the relaxation pathway that is generally adapted cross relaxation, which is responsible for positive NOE and NOE, negative NOE, where we showed double quantum and zero quantum pathways, one gives positive NOE, other gives negative NOE, which is dominant. None of them are exclusive processes, all are happening together. The dominant relaxation pathway gives you particular whether it is positive NOE, negative NOE or zero NOE. And we correlated this with the spectral density function and also tau c, which is the size of the molecule. Tau c basically decides about the sluggishness of the molecule. And afterwards we did a 1D difference NOE experiment. When the 1D difference NOE experiment pre-saturated the signal for a long time and then apply 90-degree pulse and then collect the FID and do the Fourier transformation to get the spectrum. Other case, identical condition with the identical RF power, irradiate at a far off place which is called off resonance and collect the identical spectrum for identical time and scans. Take the difference between these two. Then when you take the difference between these two, those where there is no enhancement of the signal intensity, all the peaks go to 0. The irradiated peak will become negative. And wherever there is a change in intensity, either positive or negative, that will be reflected in the difference spectrum. You can quantify this intensity and then measure the R, distance information. So this is basically the gist of NOE which I wanted to tell you. And we discussed a lot about relaxation mechanism, NOE, all are, one way or other, is information is required to understand NOE, you require relaxation. So all those things we discussed. I think next time, next class we will start with the product operators and then go to 2D NMR, there are a lot more to discuss and then go to a different topic. So I will stop at this stage. Thank you very much.